Hello everyone, this is Samuel Aremu. I am making this presentation for EC 591 paper review. I am going to be discussing about LSTNET, which is a deep learning model used in forecasting multivariate time series with long-term and short-term pattern or recurring patterns. Multivariate time series forecasting has become an important machine learning task across many domains in the past few years, including predicting the output of a solar power of a solar plant and also energy consumption and also traffic jam. Before I go into details of the model, I would share some basic definition of some terms in our time series. Time series is a sequence of observation of numerical variables indexed by a date or time stamp. It can be any data recorded over time in a sequential order, like shown in this figure. The samples were taken every 1 hour. We could see that the second value was at 1 hour away from the first value, while the second value was 1 hour, third value rather, from the second value. Okay. Examples could be the stock price, traffic data, and also solar energy data set. We also have two basic types of time series data. First, we have the univariate time series, and we also have the multivariate time series. For univariate time series, the target variable is influenced by only one factor, which is time. So we only have one variable varying over time. While in the case of multivariate time series, the target variable is influenced by multiple factors, and these factors all vary along with time. Looking at this data, for example, taking the first two columns is an example of a univariate time series, where Tx of O is the only variable. Forecasting Ts of O is based on its own past history, while taking all the columns into consideration is a multivariate time series, where forecasting is merely a combination of all variables including its own past values. Talking about trends and seasonalities, trends are long-term increase or decrease in the data. It can change direction at any time. For example, in January 2020, there was an upward trend in the sales of nose masks due to the outbreak of COVID-19, as shown in this graph. Seasonality reflects the periodic patterns that occur in the data, usually rising above a baseline and decreasing again. For example, let's consider as an increment in the amount of road user in May. That is an upward trend. But however, there are more vehicles uh, on the road in the morning and also in the evening than in the afternoon. That is a cyclic form. We also have short-term and long-term patterns, and I'll be explaining with this figure. This figure shows the data set of a traffic. There are two types of pattern shown in this figure. We have daily pattern and we also have a weekly pattern. Daily pattern I have labeled in yellow, in this yellow box, while the weekly pattern is the one in this red box. The daily pattern reflects the morning peaks and evening peaks, while the weekly pattern reflects the workday and also the weekend. As we can see, on Monday in the morning, this is the peak, while in the evening, this is the peak. Then we can see the peaks during the week, and we can see the peaks at weekend. This is a cyclic or seasonality or both short-term and long-term patterns. Another example is a typical solar energy dataset. Long-term patterns reflect the difference between day production and also night production. And short-term patterns might reflect the effect of sun or cloud movement or sun movement. The motivation for this model is for accurate time series forecasting. Time series model must be able to capture and differentiate between short-term and long-term interdependency pattern of the variables. The common autoregressive models like the autoregressive integrated moving average, popularly known as Aremu, and also vector autoregressive model fails to capture this short-term and long-term dependency among variables. With the LSTNET model, the researchers were able to achieve state-of-art results on 3 out of 4 popular datasets, which I will mention at the end. I will show you the result of the research. Given that we have values of variables at different timestamp from y1 to y of t, where t is the timestamps, and each y is a vector that has a length which is equal to the number of variables. To predict yt of h, we formulate matrix y to range from y1 equals to y of t, where h is the horizon. Similarly, to predict yt plus 1 plus h, we formulate our matrix to go from y1 to yt plus 1. There's an increment in the time taken. For convention, the input matrix is given as X, where X is a matrix of n by t, where n is the number of variables in the data and t is the timestamps, which could be 24 hours, 2 days, 1 year, 2 years. Also, in most cases, the horizon as defined here is chosen according to the personal demands. For example, for traffic usage, um, hourly horizon or daily horizon might be important for the forecasting task. As mentioned earlier, the aim of this model is to capture and consider the short and long-term pattern while forecasting. To do this, the researchers used a CNN layer, RNN layer, and also an autoregressive layer. CNN models have shown outstanding performance in the field of computer vision by extracting local and shift invariant features of the input image. That is to say that no matter the location of the target image in the image, the CNN will still able to identify the future. And also the RNN layer is used to extract long-term dependency pattern among the variables. And also as part of the overall model, LSTNet model acts an autoregressive model which helps to mitigate the non-linearity of the deep neural network output. We're going to be discussing about the CNN block here. The CNN layer is used to extract short-term patterns in the time dimension, as well as local dependency among the variable. This is similar to a normal convolutional operation on image data. But however, here each variable is seen um, each variable is seen as a channel, and a 1D filter is applied to each variable to result into these feature maps of n, depending on the number of filters applied on the input time series data. The convolutional layer is not followed by a polling layer as usually accustomed with, and causal padding was applied to the left of the input matrix to have a dimension of n by t, where n is not the number of variables and t is the original time step plus the zero padding applied to the left. The padded input matrix is then convolved with multiple filters of dimension n by w to give an output shape of Vc by T, where Vc is a number of filters applied to the input data. And the output of each future maps is given as this, is passed through this ReLU activation function, and which is Wk uh, with X, which is the input matrix, and bias. The convolutional features extracted in the same block are simultaneously fed into the recurrent component and also the recurrent skip component, which I'm going to be discussing in the next slide. The main difference between CNN and RNN is that RNN is actually incorporated with memory to take information from prior inputs to influence the current input and also the output. The recurrent component used here is a gated recurrent unit, which uses the ReLU activation function as the aiding the candidate update activation function rather than the standard than H. The researchers found that using ReLU leads to more reliable performance during backpropagation as it returns as a squashed number in between 0 and the maximum of the value, rather than returning -1 to 1. The gated recurrent units are very similar to the well-known LSTNET. They also use gates to control the flow of information. The three gates of LSTM are replaced by two gates, which are the reset gate and also the update gate. The reset gate is responsible for short-term memory, and it also controls how much of the previous information from the previous state is combined uh, with the new input. The update gate is responsible for long-term memory and determines how much of the previous information from the hidden state previous hidden state is to be kept. Due to smaller gates in the JRU model, they usually train faster than the LSTM model due to fewer or smaller parameters. Let's see how the operation is carried out. For the reset gate, the input matrix ST and the previous hidden state is concatenated and also passed through the segment activation function. We have the formula here, where WXR is the weight assigned to the input matrix and WHR is the weight assigned to the previous hidden state, and BR is the bias. And also for the update gate, ST ST and the previous hidden state is also connected together and pass through a segment activation function to give us E of t. And this is the formula where Wx of u is the weight assigned to the input matrix, and Whu is the weight assigned to the weight of the previous hidden state, where B of u is the bias. And also for the current candidate state, S of t S of t is added an element-wise operation is done here with the matrix of the reset gate, and also concatenated with the previous hidden state. And as is shown here, the weight of the input matrix is given as WSC. The weight of the previous hidden state is given as WC, and where BC is the bias. To get the current hidden state and also the output, this operation is carried out here. 1 minus one minus u of t, which is the update gate, the matrix of the update gate, is operated on here with the output of the candidate state. As you can see here, we have 1 minus u of t from here, this side, element-wise operation with the former hidden state, and also the uh, the update gate matrix. The current skip component. It was noticed that for very long input sequence, GRU fails to capture very long-term dependency of the variables. The researchers proposed a novel recurrent skip component which leveraged the periodic pattern of the data to resolve the problem. For example, to predict the traffic at 8 a.m., more leverage should be given to the traffic at 8 a.m. in the previous days rather than using the previous timestamps. The recurrent skip component does exactly the same thing with the recurrent component, except that more leverage is given to the parameter at the same time. And this is where the parameter P is introduced. So instead of having picking the exactly the previous hidden state, we have a hidden state of T minus P. Like I said, to predict the traffic at 8 a.m. tomorrow, we do h of t minus 24 hours to check on the previous hidden state candidate of 8 a.m. the previous day. And also the output of both the recurrent and recurrent skip output are combined in this dense layer to have this formula. And also, in case of non-seasonal data, an attention layer is proposed instead of a current skip layer. So some data don't have like recurring patterns. So to determine the value of P might be difficult. So in such case, an intention mechanism is used, which learns the weighted combination of the hidden representation at each window position of the input matrix. The final component is a simple autoregressive layer which adds an linearity to the non-linearity of the deep neural network. And the final output is a sum of the deep neural network here and also the autoregressive model, which is y hat of t. This is the result of the research being carried out using LSTM model. It was shown that using the LSTM skip without the attention layer, it was able to, and forecasting for the next 12 hours, the model achieved a state-of-art result when compared to other previous model. And also with the attention layer, it also achieved state-of-art result on 3 hours prediction, 6 hours prediction, and also 24 hours prediction. And it only failed on the exchange rate data set. So from this result, it is seen that the LSTNET model was able to three achieve state-of-art result on 3 datasets out of the 4 datasets used. For more information about the model, these are the references I used in preparing the presentation. Thank you very much.